Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Lesson 7. Hello. General pyramids and cones and their cross sections. Okay, classwork opening exercise. Group the following images by shared properties. What defines each of the groups you have made? So just take a few minutes and pause the video, see if you can do this, and then come back. And okay, so here we go. And if you read ahead, there's a bit of a hint. There's cones and there's pyramids, and there's what we were dealing with in exercise or module 3, lesson 7 was doing horizontal slices to the base, giving us congruent shapes. And so let's start with that. So if I took this kidney bean shape and cut it in the middle, and the plane that I cut was parallel to the base, then the piece that I cut would be congruent to the base. So forming a congruence would be here. If I cut this triangular prism horizontally with a base, I'd get a congruent triangle. If I cut this, let's say up here, like so, well, obviously it's not congruent, it's a lot smaller. So that is not going to be congruent. Same with this one here. If I cut this here, that would be a triangular prism, okay? The base would be similar to the piece I cut, but the piece I cut is obviously smaller. So it gets smaller as we go up. So I'm going to skip that for now. Same with this one. This one here would be congruent no matter where I cut it. As long as my cut is horizontal to the base, I would get a horizontal segment. Same goes with this L-shaped figure. Okay. So, and then this one comes to a point. So there are our two categories. So if it comes to a point, we get similar segments, but not congruent segments. The segments we cut would be smaller as we go up. So, oops, this one, and 8. So there is our grouping. Horizontal cuts forming congruent are red, forming similar shapes are in blue. Okay. So down below it says rectangular pyramid definition. Given a rectangular region B in a plane E and a point V not in E, the rectangular pyramid with base B and vertex V is the collection of all segments VP for any point P in B. Okay, kind of went over that last section, lesson 6. And then general cone says let B be a region in a plane E and V be a point not in E. The cone with base B and vertex V is the union of all segments VP for all points P in B. See figure 1 and 2. So figure 1 is here. Figure 2 is here. Those are not cones. What do they mean by see figure 1 and 2? Figure 3 is a cone. Figure 4, well, not really a cone. Figure 8, they come to a point. 5, 4, and 3 come to a point. See figures 1 and 2 for general cone. Okay, let's further narrow these down, by the way. So let's look at the ones I circled in red. Figure 1 and figure 2 have odd bases. They're just a particular shape. Figures 2 and 4 are, or 2 and 7, I mean, are a different kind of shape. One's a triangle and one is kind of rectangular. Okay, so these are prisms. So I'm going to call those prisms. These two are prisms. So then if I erase these, so let's narrow this down even further. Let's make subsets of the sets I've already made. And let's choose a different color. How about green for this one? and green for this one, then these are general cylinders. Okay, we don't really have a name for them. This is kind of kidney shaped, and this, I don't know what you would call it. So these are general cylinders. Okay, these two are prisms. All right, so then we look at, let's see, let's erase. Well, if we look at 4 has a square base, and 5 has a base that is a pentagon. Okay, but 3 and 8 again have odd shapes like 1 and 6 did, but these come to a point, and so do these. So the blue ones we can call cones that come to a point with polygon bases. Okay, polygon base that come to points. So this is a polygon base that comes to a point. This is a polygon base that comes to a point. But figures 3 and 8 are these shapes. They're general shapes, general cylinders again, that come to a point. Figures that come to a point with curved bases. Okay, so let's say curved bases that come to a point. Okay, and let's just leave it at that. Okay, so here's page 2 with some figures. And if I go back now and look at this last thing, it says see figure 1 and 2. They weren't talking about prior, they're talking about future, next page. So let B be a region in plane E. So here is B, this shape, in a region that's in plane E, okay? And V be a point not in E. Then I put V up here. Obviously, it's above this plane E up in space, okay? Then it says the cone with base B and vertex V is the union of all segments VP for all points P in B. So what they're basically saying is no matter what point we choose on here and we draw a line from it up to V, this is our result over here. And these, so this would be point P, this would be point V, this is point P1, P2, P3, P4, and so on. Any point P, drawing a straight line segment up to V, would give us this shape decreasing in size until we get to this point V. Okay, so that was just what they were saying right here, right? General cone. So we went from figure 1, we put a point V up here, and we drew multiple segments PV around the base. All right. Okay, so if we have a geometric shape that we have a name for, like this is a rectangle, then this would be a rectangular pyramid. This is a rectangular pyramid. But this shape here, there is no name for it. It's just a general shape. So we would just call that a cylinder, if you will, a general cylinder with a cone shape. So that's the difference between a general cylinder here and a rectangular pyramid here. Okay, or some name like a triangular. You could have a triangular pyramid, a rectangular pyramid, which is shown below. We could have a 5-sided base coming to a point, and that would be a pentagonal pyramid, and so on and so on. So just like general cylinders, general cones are named by their bases as well. So you can call it a pyramid or a cone. A general cone with a polygon base is called a pyramid. Examples of this include a rectangular pyramid or a triangular pyramid. So these are rectangular pyramids. And this one here, notice the point is offset. So if I dropped a lateral, it would not hit the center of the rectangle where the diagonals meet. But over here, this is uniform. And as we go up, the base shape would be similar to every slice that we would cut horizontal and parallel to E, or base B. In this case, we have the sides are different, okay? And the sides are called lateral faces. So these lateral faces are not congruent. One is steeper than the other, so therefore they're stretched out longer. So this set line from here to V is longer than this line from here to V. But over here, these four edges or lateral faces are congruent. Every triangle side is a congruent triangle because they share the opposite sides anywhere are congruent. So this might be longer than this side unless they're a square pyramid. Okay. Okay, so in figure 5, we're going to name things. So if I choose a segment and let's make it red, then I have, alrighty then, choose this, choose this, choose this, choose red. And if I draw a segment from A to B, and then from B to C, and then from C to D, and then finally D back to A. Well, that is, let me just fix DA. That is the base. Okay, so this is a rectangular base. Okay, but then if I take and choose a segment now and draw a segment from A to V and from B to V and from A to B, then that is the front face of this pyramid. Just fix this a little bit. There we go. And that is a lateral face, and it's in the shape of a triangle, and it is a triangle. So if the base is a square, then all of these lateral faces are congruent. If it is a rectangle, the opposite side, so ABV triangle, would be congruent to CDV, but BCV would be congruent to AVD. Okay, they're congruent, opposite sides are congruent, but not all four, unless the base is a square. Okay, so let's name all these lateral faces. So let's start with the left, go right, and go up. So we have triangle ABV. We have triangle BCV. And we have triangle the back, CDV. And we have the left side, DAV. These are all lateral faces. The base is a parallelogram, A, B, C, D. Okay, so now if I focus on edges, if you will, so if I erase or delete, let's delete this green one and this green one and just focus on the one green one, then segment BV is a lateral edge. And so is CV, so is DV, and so is AV. Lateral edges. Okay, figure 6 is a three-dimensional dilation. So as you can see, we have a base B and a base B prime, which is a horizontal. E prime is horizontal, and so is E, so they're parallel. E is parallel to E prime, the two planes. So that makes the base B and B prime parallel. And since they're parallel, and any segment from B to V will intersect a point on B prime, and the BV dilated R by a scale of R would be B prime V, for example. Okay, so these work very similar to a two-dimensional dilation, but a three-dimensional dilation is in a set line, very similar to a two-dimensional dilation. The only difference is we can see that there is another plane cut out to make it a three-dimensional shape. And a better way to represent these three-dimensional slivers, if you will, would be to use like clay, modeling clay, and to create a shape that is the same all the way up through and just tapering. And when you cut sections out of it, they are congruent. Okay, page 3 brings us to our first example. So we're now going to apply the principles of dilation in a three-dimensional shape and do examples. So this is now an application. So it says, in the following triangular pyramid, a plane passes through the pyramid so that it is parallel to the base. So we know that A prime B prime is parallel to AB, B prime C prime is parallel to BC, and A prime C prime is parallel to AC. And since they're parallel, then the angles have to be congruent because AV is a transversal and we have corresponding angles. Okay, so it is parallel to the base and results in a cross section of that triangle A prime B prime C prime. If the area of triangle ABC is 25 millimeters squared, so this triangle down here has an area of 25 square millimeters. What is the area of this triangle up here? So it's obviously less. So I know my scale factor R is going to be between 0 and 1 since it's scaling it down. And I'm given side A prime V as 3 and AV as 5. So since this is a scale factor, then we have a proportional or a ratio of 5 to 3. So be careful and make sure that you put the correct fraction setup. Do not put 5 over 3. That it would be if A, B, C was our pre-image and we dilated it out larger. But our image is A prime, B prime, C prime, and our pre-image is A, B, C. So we're going from large to small. So my scale factor has to be between 0 and 1. So I put 3 over 5. Okay, now be careful with this because we're talking about area. And I can't stress enough that what we now know is that the area of triangle ABC equals 3/5 the area of triangle A prime, B prime, C prime, but 3 and 5 are a side. And since we're talking about area, we need to take 3/5 and square it. So triangle A prime, B prime, C prime is going to be 3/5 squared times triangle ABC. So area of triangle A prime, B prime, C prime is going to equal 3 squared over 5 squared times triangle ABC's area, which is 25 millimeters squared. So when I square my scale factor, the 25s will cancel, and I now know that the area of triangle A prime, B prime, C prime, and there should be a triangle here, equals, these cancel, and I get 9 square millimeters. So the area of the smaller triangle is 9 millimeters squared, where the base was 25 millimeters squared. Okay, example 2. In the following triangular pyramid, a plane passes through the pyramid so that it is parallel to the base. That is the key to these. The base has to be parallel. Bases have to be parallel. That results in the cross section of A prime, B prime, C prime again, the triangle. The altitude from V is drawn. So there's the altitude going through perpendicular to each base and straight parallel or perpendicular to the bases. All right. The altitude from V is drawn. The intersection of the altitude with base X and intersection of the altitude with the cross section X prime if the distance from X to V, okay, the base all the way down here up to V is 18. The distance from X prime to V is 12. And the area of triangle A prime, B prime, C prime is 28 millimeters. So it's this one. They're telling us what the image area is, not the pre-image. So be careful. It's asking what the area of triangle ABC is. So we are dilating up. So our R is going to equal, our scale factor is going to be greater than 1 because we're going from smaller to big. So put the 18 over 12. We can just leave that 18 over 12, but since they're both factors of 6, that would be 3 halves. Okay, so if I want to know the area of triangle ABC, so I'd write the area of triangle ABC. Well, that equals 3 halves squared the area of triangle A prime, B prime, C prime. So the area of triangle ABC is equal to 9/4 what triangle A prime, B prime, C prime is, which is 28 square millimeters. The 4 will go into 28 7 times. So that makes it easy. The area of triangle ABC is therefore 63 millimeters squared. So it's larger than the pre-image, which is up higher. Okay, page 4 brings us to an extension, and here is a triangular pyramid, base ABC, cross section A prime, B prime, C prime, with a vertex V. Look at plane ABV. So let's draw plane ABV. Let's highlight that. So here is A, B, V. It is the lateral face that's in front of us. Okay, it's this triangle. Okay, can you describe the dilation of this plane that would take AB, the base, edge, AB, to A prime, B prime? Okay, so we want to take, let's change the color of the base now to blue. And we want to take that to this line. Okay, so we're comparing AB to A prime, B prime. All right, so the dilation would have center V and a scale factor of K, or R. In our case, we've been using R. R equals A prime V is to AV as B prime V is to BV. Okay, we can do the same with BCV and the same with ACV, but let's just focus on the front here. So if A prime V over AV equals B prime V over BV, then what can we now say? So let's just get rid of this R equals here. It's the scale factor. Okay, so now let's focus on, let me just move these. We'll move this over to here. And we'll move this over to here. So now we're focusing on BC is to B prime, C prime. So now I can say BV, which is right here, B prime V, which is this, is to BV as C prime V is to CV. So now we have all three, because the backside's already, basically we could continue with that and say CV is to AV, and we're back to over here. So since these are all equal, we have a proportional setup, then we can basically say that triangle A prime, B prime, C prime is similar to triangle A, B, C by side, side, side similarity. So I could say that by SSS similarity. All right, and the same goes with this over here, so I'm not going to continue with these because it'd be tough. I'd have to call this P sub 1 V, P sub 1 prime V, and so on, and it's much more tedious, and there's multiple line segments, so it's the same concept as this, so I'm just going to continue with the exercise. And it says the area of the base of a cone is 16 and the height is 10. Find the area of a cross section that is a distance 5 from the vertex. Okay, so we can do this without a diagram if we know what our scale factor is. And the area of the base of a cone is 16 and the height is 10. And find the area of a cross section that is a distance of 5 from the vertex. So if we have a vertex, this distance is 5, and the base down here, the whole distance is 16, just to give you a quick picture of what's going on here. That's just 2D, but you get the idea. So what's it asking for? Find the area of the cross section. So if we had a third side over here, it'd be like this. So this cross section here. All right, so it's smaller, so my scale factor is the smaller number on top of the larger number. So the numerator has to be less than the denominator to be between 0 and 1. We're scaling down. So R is 5/16. So we take that R and we square it. And the area of the base of a cone is 16 and the height is 10. Oh, I made a mistake. The area is 16. So this area of the base is 16. The height is 10. So 5 over 10 is our R. Sorry about that. And that reduces to 1/2. The area is 16. So the area of the smaller section equals 1/2 squared the area of the smaller. Let's call it just A prime. So the area, take that back, the area of prime, the smaller one, A prime is 1/2 squared of A. A prime is going to be 1/4 of A, and the area of A was 16. So 1/4 of 16 is simply 4 units squared. Okay, page 5 brings us to example 3, and it says general cone cross-section theorem. If two general cones, so we have two cones here, one is a circular shape and the other one is a rectangular shape. If two general cones have the same base area, so if the area of this was, say, 20 units squared, then this is 20 units squared, and the same height, then the cross sections for the general cones, the same distance from the vertex, will have the same area. State the theorem in your own words. So try to answer this, pause the video, and see how you do. So here is one of the possible situations we have. The theorem is saying that if two cones have the same base area and the same height, then cross sections of both solids that are the same height from the vertex should have the same area. So it's just rewording this a little bit. So we'll use the space below to prove the general cone cross-section theorem. Okay, so here goes, proving this. So let the base of the cone B and C in the figure be such that 1, area of B equals area of C. Okay, that's our starting point. So we know the area of each base is equal. They're congruent. 2, the height of each cone is h. And 3, the distance from each vertex from B prime to C prime are both h prime. So what they're saying here is if I take a segment and draw it from this point straight down perpendicular to the base, and I copy that and make it the exact same length and put it in here, then the height of both of these is equal. They're both going right down and they're perpendicular to the base, like so, 90-degree angle. So these distances, these h's, are congruent. So the height of each cone is h. So I'll call this h and call this h. And 3, the distance from each vertex to B prime and C prime are both H prime. So the distance to B prime from the vertex V is H prime. The distance from the vertex V to C prime is H prime. And they're the same distance. They are equal. So if this red segment here is 10 and 10, and this is 4, and this is 4, then we can conclude, how do we show that the area B prime is equal to area C prime? Okay, well, we can say that the area of B prime equals H prime over H, okay, the ratio, scale factor of area B. So B prime is equal to H prime over H times the area B, and you have to square that like we've been doing. We do the same over on the other side. Area C prime has to equal H prime over H squared times the area of C. Okay, since the area B equals the area of C, then area B prime has to be equal to area C prime because H prime over H squared is equal. So if I could cancel this with this, and if I know that area B is already equal to area C from up here, a given, then obviously if they're equal, they have to be equal to their primes. Okay. Exercise 2. The following pyramids have equal altitudes. Okay, so the distance from V straight down to the base, in other words, if I did what I did in the last proof, and I draw a segment from V down to a point on the base, like so, that is perpendicular. And I copy it, same length, and I bring it over to the point S, perpendicular to this here would be in line, same height as this base, but it's outside because it's pulled over, okay? So the pyramids have equal altitudes, and both bases are equal in area and are on the same plane. They're coplanar. So picture a plane, this piece of paper, and this base B, C, D, A, B, C, D. Here's A right here. This is the base here. Okay. Let me draw that because this is a confusing looking diagram. So let's just highlight the base. Here's A, here's B, here's C, and here's D. So this is the base we're talking about. And it's following my pen when I draw it. So let me fix this. Okay, so there's the base A, B, C, D, and we're going out at an at an angle straight out. So we're getting smaller this way. So picture a box on the ground or a tunnel, and this one the same way. So this base is, I'll do it in blue as well, is TU V W X Z, what's this one? That's X prime. TUVWX. They didn't label Y, but it's right here. Over to Z, and then back to T. So there's our base of our diagram on the right. Okay, and that is being stretched out. So we are scaling down as we go. Think of a tunnel going off in the distance, getting smaller and smaller from our vision. All right, so the following pyramids have equal altitude. Okay, same altitude. It looks like they're going back, but they're going up. And both bases are equal in area and are coplanar. So these are on the same plane and they're the same area. Both pyramids cross sections are also coplanar. So the cross sections are back here and they're parallel. If BC is 3 square root 2, so BC is right here and it's the length 3 root 2, and B prime C prime, which is back here, from here to here, is 2 square root 3. Okay. And the area of TUVWXYZ is 30 units. So this blue area here is 30 units squared. What is the area of the cross section A prime, B prime, C prime, D prime? Okay, so we don't need the area of this. Well, we do. We know they're congruent. We know that the areas are equal. Both bases are equal in area. So this is 30. So the area of A, B, C, D is also 30 units squared. Okay, so this is 30 units squared. We're scaling down, so our R is going to equal the smaller number, 2 root 3 over 3 root 2, and we have to square those. And if we take those and multiply them by the area of ABCD. So let me see. Let me just leave this. Let me undo some of this. There's my R. R is 2 root 3 over 3 root 2, my scale factor. And if I know that the area of, what are we trying to find? A prime, B prime, C prime, D prime. So the area of A prime, B prime, C prime, D prime is going to equal 2 square root 3 over 3 square root 2 squared times the area of A, B, C, D. So the area of A prime, B prime, C prime, D prime equals, now careful with this, you need to distribute. So 2 times 2 is 4, and, or 2 squared, I should say. And the square root of 3 squared is 3 over 3 squared, which is 9. Square root of 2 squared is 2 times the area of ABCD, which is 30 square units. So the area of, the area of A prime, B prime, struggling here with my pen, B prime, C prime, D prime equals 12 over 18 times 30 units squared. Okay. So let's just make this a smaller number. 18 will become 9, 3 will become 15. 3 will go into 9 3 times, 3 will go into 15 5 times, and 12 divided by 3 is 4. Okay, so I have a 4 and a 5 remaining, so that makes it much easier. No calculator required. A prime, B prime, C prime, D prime equals 4 times 5, which is 20 units squared. And that is the area of this rectangle here. Okay, page 6 brings us to the end of lesson 7. Review the lesson summary and go to your problem set.